In today's video, we're going to talk about the chemistry of sulfur-containing molecules. And we're going to start with thiols, which are the sulfur analogs of alcohols. And since alcohols react as nucleophiles, thiols also are generally going to react as nucleophiles. So if we look at this example, we have propane thiol, which has an SH bond like an alcohol would have an OH bond. And much like alcohols, the H attached to a sulfur is quite acidic. And so if you react that with a base like sodium hydride, the first thing that's going to happen is that the electrons on this hydride are going to attack that H, and this the electrons in the SH bond are going to be given to the sulfur. And so you would get an intermediate after step one that looked like that. And when you add this anion to 1-bromobutane, you're going to get an SN2 reaction. So 1-bromobutane, we've got butane, and the bromide is on carbon 1. And so your sulfur, which is a good nucleophile, especially with a negative charge, is going to attack the carbon with the bromide. The bromide is going to leave. That's going to leave you with a sulfide, which would be an ether analog of, or a sulfur analog of an ether, where we have the propane group here that came from our thiol and the butane group here that came from the alkyl bromide. It's worth noting that this reaction would probably take place even without sodium hydride, that thiols are great nucleophiles, and so we might expect that a thiol without sodium hydride would directly attack that alkyl bromide to produce the same thioether or sulfide. Before we talk more about the chemistry of sulfur-containing molecules, I want to take a moment to take a detour and talk about an important thiol in biology, and that is this alpha amino acid, cysteine. Cysteine is one of the alpha amino acids that are incorporated into the structure of proteins. And they're alpha amino acids because the amine group here is on the alpha carbon. This is the alpha carbon to the carbonyl here, or the carboxylic acid here. So the amine group is on the alpha carbon, and in this case, on the beta carbon, we have a thiol. So cysteine is an alpha amino acid that is incorporated into the structure of proteins. And it's a amino acid that has some important implications in the tertiary and quaternary structure of proteins. And so cysteine residues can be oxidized inside a protein. And when this undergoes oxidation, you form what's called a disulfide bond. And a disulfide bond is similar to a peroxide bond or an OO single bond, except that it's sulfur instead of oxygen. So these two sulfur atoms have been oxidized, and the bond that they form is called a disulfide bond. These bonds are much stronger than an oxygen-oxygen single bond, and they are important in the folding and tertiary structure of proteins. Amino acid cysteine can also be the target of heavy metal poisoning in proteins as well. And so, if you think about heavy metals, some examples of those might be mercury, 2 plus, lead can be implicated in heavy metals poisoning as well. And mercury and lead are both great Lewis acids, and the SH bond, or the sulfur, has some electrons. It can act as a Lewis base. And so the electrons on sulfur can attack that metal, or a generic metal, and you might get a structure that looks like this. In this case, we attacked mercury, so we'll go ahead and keep a mercury here. And when sulfur attacks a mercury, the proton on it becomes quite acidic, and so it might fall off, which is going to make this sulfur-mercury bond quite strong. And when these heavy metals bind into this free thiol moiety that's embedded into a protein, it disrupts the protein structure and can cause misregulation or misfunction of the protein. And so if we take a moment to look at this starting material, this AA is just an abbreviation for amino acid. So this is in the middle of a long amino acid chain, or in the middle of the protein chain. And what we're looking at here is an amide. That's the functional group that has a carbonyl attached to a nitrogen. But you might also hear this called a peptide bond. And that is the bond that attaches two peptides, or two amino acids, together to help make an long amino acid chain. Now that we've looked at the chemistry of an important thiol in biology, let's return to some other sulfur-containing molecules. This time we're going to look at sulfides. And in the first slide, we made a sulfide by forming what looked like a thioether, or a sulfur analog of an ether. And these things react as nucleophiles. So sulfides or thioethers react as nucleophiles. So again, sulfur has two or lone pairs, and we can use one of those as a nucleophile. And so we're going to take these electrons, they're going to attack that CH3, which is going to kick off that I minus. You're going to get this sulfur with a positive charge on it, because it's got 3 bonds. Much like oxygen, sulfur prefers to form 2 bonds, but it can form 3, and when it does, it gets a positive charge. And we also have a I minus floating around as well. So sulfur atoms can get alkylated, or we can add an extra alkyl group so that it's got 3 carbons coming off of it. It's got a positive charge, and this thing is called a sulfonium ion. And these are substantially more stable than their oxygen analogs. Sulfonium ions are the last class of sulfur-containing molecules that we're going to talk about today. And unlike the other 2 sulfur-containing molecules, sulfonium ions react as electrophiles, or in this case, an alkylating agent. And that's just a chemistry word for attaching an alkyl group to another molecule. And so in this example, we have a simple sulfonium ion, a sulfur with 3 methyl groups on it, reacting with methanol. And methanol is going to be our nucleophile in this case. So it's got some electrons on oxygen. And those electrons are going to attack the carbon of one of the methyl groups on sulfur. It doesn't matter which one in this case because they're all the same. And then the bond that's holding that carbon to sulfur is going to kick down back to sulfur so that we get an intermediate like this. And we still have our sulfur with now just 2 methyl groups attached to it. And in a second step, you might add some sort of base to deprotonate that H off of the methyl. So we can add, say, triethylamine. And that's going to grab this proton so that we form a methyl ether and the thiomethyl ether as well. In addition to sulfonium ions, chemists have a variety of other methylating or alkylating reagents that are actually probably a little more common than sulfonium ions. So methyl iodide is a common alkylating reagent shown here, and it reacts like an SN2 reaction with, in this case, a sulfur, but in general, any nucleophilic compound to give this intermediate, and then some base would have to come in and pluck out that proton to give you the sulfide or thioether shown here. And methyl triflate reacts in just the same way. So this is methyl triflate. And it again reacts with nucleophiles, in this case an amine, to kick off a triflate leaving group. That's going to give you plus a triflate leaving group, which looks like this. That nitrogen has a positive charge. And again, some base would have to come in and pluck this off. To create now a secondary amine. It's actually quite difficult to get this secondary amine. Likely that would keep reacting to form a tertiary or maybe even a quaternary ammonium salt from there. Well, chemists don't often use sulfonium ions as methylating reagents. Biology does. Biology uses sulfonium ions to methylate things like nucleic acids and proteins and amines in their biosynthesis. And these alterations can be important in the function of the molecules being made. And to do this, biology uses the amino acid methionine. This is another example of an alpha amino acid. And so this amine is on the alpha carbon to that carboxylate or carboxylic acid. And this time, rather than the sulfur being on the beta carbon, it's on the gamma carbon. And this sulfur, unlike cysteine, has a methyl group attached to it as well. And methionine reacts with ATP or adenosine triphosphate in enzymes that are specifically for synthesis of SAM or S adenosynyl methionine. And this reaction takes place probably not quite this simply, but we can sort of see some of the electron transfers happening when sulfur attacks this carbon of adenosine triphosphate and kicks off this phosphate leaving group. That forms this sulfur carbon bond and kicks off some phosphate, this diphosphate group and this monophosphate group. And the cleavage of this monophosphate group is likely what provides the energy to form this high energy SAM intermediate. And this SAM intermediate is what gets used to methylate a variety of biocompounds. Once SAM or S-adenosynyl methionine is generated, another enzyme, a methyltransferase, can take SAM and use it to methylate a variety of substrates. And in this case, we're looking at the methylation of norepinephrine to produce epinephrine. If we look at how the electrons are moving, the electrons on nitrogen are coming in and attacking this methyl group, which is kicking that sulfur off, and that forms epinephrine and S-adenosyl homocysteine, which can be used to regenerate SAM, and epinephrine is responsible for an adrenaline rush. That's going to wrap up our discussion of the chemistry of sulfur-containing molecules.